Well, during that last video, I was saying that I was probably going to do one more handout and video on volume of revolution, but I think in the interest of time, we'll move on from volume of revolution. If you want to see some additional problems or you have any questions, just let me know. But I think what I'd like to do is to move on and talk about arc length, and then also in the next one we'll talk about surface area. They're very closely related to each other. In fact, the formula for arc length shows up in the formula for surface area, but we'll talk about that in the next video. So here's the formula for finding arc length, and so this is going to be the integral of the square root of 1 plus the derivative of the function squared. Okay, first let's see where the formula comes from, and then we'll talk about using it to solve some problems. So where does the formula come from? Well, so here's our f of x function between a and b. And the idea is, again, we want to chop it up into little pieces. So let's just look at one of these little sections right here. Okay, so this is going to be x of I and x of I plus 1, and they're going to run all the way between a and b. So the idea here is that if we look at this little tiny, what's essentially a right triangle here, now this piece, we've talked about this for most of these integrals, is that this is delta x. The other thing is that this over here is delta y. So a good approximation, I mean, I said a minute ago it's a right triangle. It really isn't, because this hypotenuse is not really a straight line. But that's really the basis of calculus, is that we're approximating these curves with straight lines. So what we've essentially got then is we have this pseudo right triangle with one leg as delta x and the other leg as delta y. That means the hypotenuse is going to be the square root of delta x squared plus delta y squared. And so now hopefully you're seeing, oh, where is the square root coming from? Where is the squared coming from? It's coming from the Pythagorean theorem. Okay, and so really, so let's see. So now we want to sum this up. Let's see, I'll put that down here. So we're going to take the sum as I runs from 1 up to n between a and b, and then take the limit of that as n goes to infinity. And all we're going to do is sum up all of these little pieces, delta x squared, square root of delta x squared plus delta y squared. Now the difference between this formula and this formula is that to make this nice, to make it involve the function, we come over here and we multiply this by delta x, the square root of delta x squared over the square root of delta x squared. So what does that do? Well, in the numerator, that becomes delta x. So let's put this all back in here. Oh, that's a delta x squared, delta y squared. And over here, that's going to be delta x. The square root of delta x squared is just delta x. This other one goes into the denominator, okay, so that we can then introduce it into the square root. Let's see, let's move down here. And so now we've got this. This will be delta x squared over delta x squared, delta y squared over delta x squared. So here's the 1. Hopefully I won't run out of room here. Square root, there's the 1 right here. And then this is delta y over delta x all squared. And we've got a delta x out here. So this is the derivative, right? This is essentially dy over dx squared. If we move from the sum to the integral, then this is dy dx, which is the same thing as f prime of x. Okay? So that's where we get the 1 plus f prime of x squared, and then this delta x on the end, there's our dx. So something else that I'm going to kind of continue to bring up as we're working through this first half of Math 253 is that when we first started talking about integration, we introduced it as the area under a curve. And that was true at the time. But since then, we've seen it do other things. You know, we just finished doing the volume of revolution. Now we're talking about arc length. In the next video, we're going to talk about the surface area of revolution. And then after that, we'll talk about center of mass. And all of these things, right, we're creating a way to make these calculations based on these summations. So anytime we get this set up, anytime we can set up a calculation with a limit of the sum with our involving the delta x and the function that we're working with, then we can, that limit will pass into an integral. Okay? And it's really a fundamental idea of integral calculus is that it's not just the area under the curve. It's any calculation that you want to make that involves these delta x's and the function values. Once you can set up something like this, then you can calculate it as an integral. I'll talk about that more as we continue to work with these ideas. But it's just, it's something that people sometimes don't realize. They think of integration as only the area under the curve, whereas it's actually a process for making any kind of calculation that you want to, but it has to involve the limit of a sum and these terms that we're working with. Okay, so there's the setup for the formula that we're going to use. Now, I'm a big one for doing mathematics ourselves and not relying too much on the technology. I think it's good to use where it's appropriate, but I'm always wanting us to maximize how much math we do ourselves because I think that that's really important. Now, having said that, this formula generates some really difficult integrals. Okay, and so in looking at some old textbooks that I have before the days of graphing calculators, they all were in this particular format so that when you plugged them into this formula, you could do the integral yourself. But that's kind of limiting. So what I've done with this topic is to, we take a problem, let's say we want to look at problem 2 on the handout. So problem 2, we're working with the curve y equals x cubed minus 2x squared plus 3, and we want to find the length of the curve between -1 and 3. Well, let's see here. Let's take a look at what this curve looks like. X cubed minus 2x squared plus 3. So this is doing something, kind of like this. And let's see, where is 3? 3 is like over here somewhere. And -1 is just about right there. So we're looking for the length of this section right there. Okay? So what I want you to do is, and what the instructions on, let's see, I think the instructions on the handout, yeah, the instructions on the handout say this, and when I set up the quizzes, and when we do the midterm and final, it'll say the same thing, which is set up an integral that you can use to find the indicated length, and then we're going to use the graphing calculator to calculate the value of the integral. Okay, so to set up the integral, we need to know the derivative of the function. So f prime here is going to be 3x squared minus 4x, and that's it, right? When we take the derivative of the 3, that'll be a 0. Okay, so that says that our length is going to be the integral from -1 to 3, the square root of 1 plus 3x squared minus 4x all squared dx. And don't bother trying to square this out. It's not really necessary. Now, to use the graphing calculator to calculate a value for this, what we want to do is we want to go in. Now I was just using it to graph the actual function itself, so I'm going to erase that, and in its place I'm going to put square root 1 plus parentheses 3x squared minus 4x close parentheses all squared. Okay, so now that I've got that, we're going to look at a graph. Now the graph for this looks very different. Let's see here. So this graph, square root 1 plus 3x squared minus 4x all squared, looks something like this. And so what we want to do to find this integral is to go into the calculate menu. So if you do second trace, choice number 7 has this little integral sign, integral f of x dx. So choose number 7. And then it'll bring you back to this screen, and it'll say lower limit. Well, that's going to be -1. So we type in a -1 for the lower limit. And then it says upper limit, so that's 3. So we type in the 3 there. And then it calculates the value of the integral as it shades. It's going to shade underneath this thing from -1 up to 3. And let's see, what do we get there? About 15.6. And so this will be about 15.6. Okay, so that's how we're going to do these problems. We'll look at a couple more examples here. And then, like I said, when we come to do the next topic, which is the surface area of revolution, we'll be doing the same thing because that formula is also, it produces these things that are very, very difficult to integrate. Okay, so there's problem 2. Let's look at a couple more here. Oh, let's see here. Well, let's look at problem 6. Problem 6, y equals 5x minus x squared. Now this one, let's see. What is this one going to look like? It's going to have roots. It should be roots at 0 and +5. So it should look something like that. It's a parabola. It's an upside down parabola with roots at 0 and +5. And let's see, what do we want? We want to find the arc length from 0 up to 4. So that's going to be about right here. So we're looking for the length of that curve right there. Okay, so again, to do these problems, we need to know the derivative of the function. So y prime is going to be 5 minus 2x. And so then our length is going to be the integral from 0 to 4 square root 1 plus 5 minus 2x all squared dx. So now we go into the graphing calculator and we put in 1 plus parentheses 5 minus 2x all squared. And let's see what that graph looks like. So that graph is going to look something like this. And then again, we hit the second trace, choice number 7. Our lower limit is 0. Our upper limit is 4. That'll shade the thing kind of like this. And then it'll give us a value for the length there, about 9.8, let's say. Okay. Let's see here. So that's problem 6. Let's see, let's do one more here. We'll do problem 12. And this topic actually is kind of short because we're using the calculator to do most of the heavy lifting. Okay? And I do want to, I do like to talk about the derivation of the formula because it's always coming from that graph and chopping it up into little pieces. And also this concept that the integral is not just the area under the curve, but it's a calculation process that can be used for a lot of different things. Okay, let's see here. Problem 12, we've got a square root as our function. So let's see what this looks like. Y equals square root 3x plus 5, and we want to find the length of the curve between -1 and +4. So let's see here. I think I'll sketch a graph. It'll look something like this. Let me look at it on the graphing calc just to make sure that I did that correctly. 3x plus 5. Yeah, basically something like this. Okay, now, so 4 is going to be out here somewhere. -1. So this point right here where it hits the x-axis is going to be at -1 2/3. So -1 is going to be about right there. So we're looking for the length of that line right there, or line segment. Okay, so now if we want to know the length of that, we need to know the derivative here. So remember, this is 3x plus 5 to the 1/2 power. So our derivative is going to be 1/2 3x plus 5 to the -1/2. And then don't forget your chain rule. This is going to have to get multiplied by 3 because the derivative of what's inside there is 3. So this is going to be 1.5 3x plus 5 to the -1/2. So if we want to put this into that formula, our length then is going to be the integral from -1 up to 4, square root 1 plus 1.5 times 3x plus 5 to the -0.5 all squared. And do be careful about how you're typing that in there. Let's see. So we're going to do square root 1 plus parentheses 1.5, then parentheses 3x plus 5, and then we close those parentheses and get a -0.5 for the exponent, and then we close these parentheses and put the exponent of 2 up there. And let's see, what does this graph look like? Something like this. And so then if we want to find our integral between -1 and 4, then you'll see the shading under there like this. And then we'll get our answer there about 5.73. Okay, so like I said, these arc length problems are not all that tricky. It takes a little bit of getting used to, getting this entered properly into the calculator, making sure that you find the derivative correctly, and then getting used to using this feature on the calculator. Okay, so like I said, in the next video, we'll extend this to talk about surface area, and when we do that, I'll talk more about that Torricelli's trumpet that I brought up last term, and that's the figure that has a, what is it? It has a finite volume, but it has an infinite surface area. Okay, but for right now, just please do the odd problems on the arc length, and then next time we'll talk about surface area.